It was minus 230 degrees Celsius and something on the surface was moving. Not fast, not visibly, to a human eye, but moving. A haze layer, thin as breath, curled upward into a black sky lit by a sun so distant it looked like just another star. Nobody was watching, not directly. The instrument doing the watching was 5.9 billion kilometers away, orbiting a point in space where gravity balances itself between the Earth and the Sun. It wasn't supposed to be looking here at all. It was built to stare at galaxies born 13 billion years ago, to find the first light in the universe, to catch the atmospheres of planets orbiting other stars. Instead, for a handful of hours, it turned its mirrors toward a small, cold, overlooked world at the edge of our own solar system, a place most people had written off as a footnote. And what it found didn't fit. This is the real story of what the James Webb Space Telescope saw when it looked at Pluto. To understand how strange this discovery really is, you first have to understand how little anyone expected from Pluto in the first place. When Clyde Tombaugh discovered Pluto in February 1930, working from photographic plates at Lowell Observatory in Flagstaff, Arizona, astronomers had been searching for nearly a century for a hypothetical planet X they believed was tugging on the orbits of Neptune and Uranus. Tombaugh found a faint point of light shifting against the background stars, and the world had a ninth planet. For decades, that was the entire story, a distant, tiny, frozen dot, too far to study in any real detail, too small to matter scientifically, next to giants like Jupiter and Saturn. By the 1990s, as astronomers discovered more and more icy bodies sharing Pluto's neighborhood, the picture shifted again. Pluto wasn't a lonely, oddball planet. It was the first known member of an entire population of worlds, the Kuiper Belt, a frozen ring of debris left over from the solar system's formation. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet, a decision that remains controversial among planetary scientists to this day. But reclassification didn't make Pluto less interesting. If anything, it made it more important, a representative of an entire class of worlds humanity barely understood. To understand why this matters today, you have to go back further than James Webb. You have to go back to July 14, 2015, to a spacecraft called New Horizons, and to a single flyby that lasted less than a day. New Horizons launched in January 2006 before Pluto was even reclassified as a dwarf planet. It spent 9.5 years crossing the solar system, and when it finally reached Pluto, it had less than 24 hours to gather everything it could before the encounter was over. There would be no orbit, no second pass, just one high-speed sweep past a world humanity had never seen up close. What it sent back changed planetary science overnight. Instead of a dead, cratered ball of ice, New Horizons revealed a world with mountains of water ice standing as tall as the Rockies. It found a heart-shaped plain of nitrogen ice, later named Sputnik Planitia, so smooth and young-looking that geologists immediately suspected something underneath was still active. It found evidence of possible cryovolcanoes, ice volcanoes, that may have erupted not millions of years ago, but recently, on geological timescales. And it found haze, layers of it, more than a dozen distinct bands, rising nearly 200 kilometers above the surface, visible only because sunlight caught them at just the right angle during the spacecraft's departure. Nobody expected a world this small, this cold, and this far from the sun to still be geologically alive. The mission team called it the Pluto System Rewrite. Overnight, Pluto went from an afterthought to one of the most scientifically active bodies in the outer solar system. Alan Stern, the principal investigator of New Horizons, had spent over a decade fighting to get the mission approved and funded before it ever launched. In the years immediately following the flyby, he repeatedly described Pluto's revealed complexity as one of the most humbling moments of his career, a reminder that distance from the sun says almost nothing about a world's internal story. That humility mattered because it set the tone for everything that came after. Instead of treating Pluto as a solved problem, the planetary science community treated it as a door that had only been opened a crack. The haze layers were part of what kept that door open. Unlike the mountains and plains, which could at least be explained by known ice geology, the haze was chemically strange from the very first images. More than a dozen distinct bands, some visible only in the final images taken as New Horizons looked back at Pluto's night side, backlit by the sun. The haze extended far higher into the thin atmosphere than any existing model predicted, and its layered structure suggested some kind of repeating atmospheric process. Waves or temperature banding, cycling at regular intervals no one could fully explain. For nearly a decade, that haze mystery sat mostly unresolved. New Horizons had captured it perfectly, but a single flyby couldn't show how it changed over time, under different sunlight angles across different points in Pluto's orbit. But New Horizons could only tell part of the story. It was a flyby, not an observatory. It captured one moment from one angle at one point in Pluto's 248-year orbit around the sun. Whatever was happening beneath that haze, whatever was driving that nitrogen ice cycle, whatever was warming the interior enough to keep cryovolcanoes active, All of it remained locked behind a single dataset, frozen in time from a decade-old encounter. That's where James Webb comes in. James Webb was never designed as a Pluto mission. Its primary science goals sit at the opposite end of the universe. The earliest galaxies, the ionization era, the atmospheres of exoplanets dozens of light years away, but its instruments are sensitive enough, and its infrared capabilities precise enough, that mission scientists began quietly proposing something unusual, pointing the most powerful space telescope ever built back toward our own cosmic backyard. In late 2022, that proposal became reality. Using its near-infrared spectrograph, James Webb began collecting light from Pluto's thin atmosphere, a mixture dominated by nitrogen, with traces of methane and carbon monoxide. Unlike New Horizons, which saw Pluto for hours, James Webb could return to it again and again, watching for change over time. And change is exactly what it found. The methane signature in Pluto's atmosphere didn't behave the way pre-Webb models predicted. Photochemical models, the equations scientists use to predict how sunlight breaks apart and reforms molecules in a planetary atmosphere, had built a fairly confident picture of how methane should be distributed with altitude. James Webb's spectra didn't match it. Instead, researchers found unexpected concentrations of hydrocarbons at altitudes the model said shouldn't exist yet. The chemistry was happening faster, or differently, than anyone had accounted for. One atmosphere, one small, cold, moon-sized world, and a chemical process running ahead of the equations built to explain it. This wasn't the first time an outer solar system atmosphere had surprised researchers. Neptune's largest moon, Triton, shares striking similarities with Pluto. Similar size, similar nitrogen-dominated atmosphere, similar surface temperature. Voyager 2's 1989 flyby of Triton revealed active geysers erupting nitrogen gas and dark material kilometers into its thin atmosphere, driven by a process scientists still don't fully understand, solid nitrogen ice apparently being warmed just enough by weak sunlight penetrating a translucent surface layer to trigger explosive venting from beneath. If a mechanism like that exists on Triton, some researchers now ask, could something related be happening on Pluto? Not necessarily geysers, but a subtler, slower version of the same basic physics, warming ice from within just enough to keep the atmosphere and haze chemistry more active than a purely surface-driven model would predict. It's a comparison mainstream researchers treat carefully. Triton and Pluto are similar but not identical, and Triton's geysers are visually dramatic in a way nothing yet observed on Pluto has matched. Still, the parallel is part of why some scientists were primed to take Webb's atmospheric anomalies seriously, rather than dismiss them as instrument noise or model error. Stay with me, because this is where it gets stranger. Pluto's atmosphere isn't static, it's tied directly to the nitrogen ice on its surface, specifically the vast plain of Sputnik Planitia. As Pluto moves through its extreme 248-year orbit, its distance from the Sun changes dramatically, and so does the temperature of that ice. When it's closer to the Sun, nitrogen ice sublimates directly into gas, thickening the atmosphere. When Pluto drifts farther out, that gas should, in theory, refreeze back onto the surface, and the atmosphere should thin. Except it isn't behaving that way. Ground-based stellar occultation observations, a technique where astronomers watch Pluto pass in front of a distant star and measure how the star's light dims and bends through Pluto's atmosphere, have shown that Pluto's atmospheric pressure kept rising for years after the planet passed its closest approach to the Sun in 1989. By the time New Horizons arrived in 2015, scientists expected the atmosphere to be thinning. It wasn't. James Webb's newer data adds another layer to that puzzle. The distribution of haze and hydrocarbons it detected suggests the atmosphere isn't just lagging behind the temperature curve. The entire chemical cycle may be running on a delay nobody can currently explain with orbital mechanics alone. Anomaly 1. An atmosphere that thickens when the models say it should thin. Anomaly 2. Haze chemistry occurring at altitudes and speeds the photochemical models don't predict. Anomaly 3, and this is the one that pulled in outside researchers, a subtle but consistent thermal signature detected in Webb's infrared readings, hinting that parts of Pluto's crust may be losing heat unevenly in patterns that don't map cleanly onto known geological features. 3 separate data threads, 3 separate research teams, all pointing toward the same uncomfortable conclusion. Something inside or beneath Pluto's surface may still be active, and it might be more active than anyone assumed. This is where Dr. Carly Howitt, a planetary scientist who has spent years studying Pluto's thermal behavior using both New Horizons and ground-based data, enters the story. Howitt has long argued that Pluto's interior may not be as dead as its surface age would suggest. Her research, building on New Horizons gravity data, supports the idea that Pluto likely holds a subsurface ocean, a layer of liquid water, kept from freezing solid by a combination of leftover formation heat, radioactive decay in the rocky core, and a possible insulating layer of gas hydrates between the ocean and the ice shell above it. If that subsurface ocean exists, and if it is still slowly releasing heat outward, it could help explain both the unexpected cryovolcanic activity New Horizons spotted and the strange, uneven thermal patterns Webb is now picking up from orbit. It would mean Pluto isn't just a leftover chunk of the early solar system. It would mean Pluto is doing something, slowly, quietly, on a timescale almost incomprehensible to us, that keeps a liquid ocean alive nearly 6 billion kilometers from the Sun. The comparison scientists keep coming back to is Europa, Jupiter's ice-covered moon, long considered one of the solar system's best candidates for hosting a subsurface ocean. Europa's ocean is thought to be kept liquid primarily by tidal heating, the constant flexing caused by Jupiter's immense gravity as Europa orbits it in a slightly eccentric path. That flexing generates enough internal friction to maintain liquid water beneath dozens of kilometers of ice. Pluto doesn't have that luxury. It has no massive nearby planet to generate tidal flexing on the scale Europa experiences. Its only significant gravitational partner is Charon, its largest moon, and the tidal forces between them, while real, are far weaker than what Jupiter exerts on Europa. That's exactly why a still active subsurface ocean on Pluto is so much harder to explain, and why, if confirmed, it would be so much more significant. It would mean liquid water can persist far longer and under far weaker heating conditions than the tidal heating model alone can account for. It would point toward radioactive decay in a rocky core, ancient formation heat that hasn't fully dissipated in 4.5 billion years, or some combination of processes scientists don't yet have a complete model for. 12 billion years of cosmic history, 4.5 billion years since Pluto formed, 6 billion kilometers from the star that's supposed to be its only heat source. And still, something down there might be warm. You need to understand how radical this idea would have sounded even 15 years ago. Before New Horizons, most planetary scientists treated Pluto as a scientific curiosity at best, a ball of ice too small and too cold to sustain any meaningful internal activity. The idea of a liquid ocean under its surface would have been dismissed outright. Now it's one of the leading explanations on the table. But not everyone agrees on what Webb's new atmospheric data actually means, and this is where the story pulls back from speculation toward the caution good science demands. Several atmospheric chemists studying the same James Webb spectra have proposed a far less dramatic explanation. It's possible, they argue, that the existing photochemical models of Pluto's atmosphere were simply incomplete, not because something new is happening beneath the surface, but because our understanding of how sunlight interacts with methane and nitrogen at extreme cold and extreme distance was never fully tested against real data until now. New Horizons gave scientists a single high-resolution snapshot. James Webb is now providing repeated, high-precision atmospheric readings for the first time in Pluto's history. It would be unusual, some researchers point out, if that upgrade in observational power didn't reveal discrepancies with older models, discrepancies that reflect the limits of 2015-era science, not evidence of hidden ongoing geological activity. In other words, the surprise might not be Pluto. The surprise might be how little we actually understood about Pluto's atmosphere before we had a tool good enough to study it properly. This is the tension running through the entire investigation. On one side, a growing body of thermal and atmospheric anomalies that align suspiciously well with the subsurface ocean hypothesis. On the other, a more conservative read grounded in the simple fact that every time humanity builds a more sensitive instrument, nature tends to look more complicated, not because the universe changed, but because our old picture of it was too simple to begin with. Both things can be true at once. That's what makes this genuinely unresolved, rather than manufactured mystery. What isn't in dispute is the timeline of when all of this came together. The critical Webb observations were captured across several visits between 2022 and 2024, using the telescope's near-infrared spectrograph in a mode specifically designed to isolate faint atmospheric signatures against Pluto's dim, distant disk. Cross-referencing that data against archival stellar occultation records, some stretching back to the 1980s, is what allowed researchers to notice the long-term pressure trend didn't match predictions. Then, in early 2025, a reanalysis of Webb's thermal infrared channel revealed the uneven heat loss pattern that reopened the subsurface ocean debate in earnest. Meanwhile, teams working independently on the atmospheric chemistry side were preparing their own paper, unaware their conclusions were about to intersect with the thermal anomaly work. When the two lines of research were presented at the same planetary science conference within months of each other, it was not framed as confirmation of anything. It was framed as a question serious enough to justify years of additional observing time. Because that's the other detail that makes this more than a passing curiosity. James Webb has enormously oversubscribed observing time. Every hour spent looking at Pluto is an hour not spent looking at a newborn galaxy or a potentially habitable exoplanet. For a Pluto observing program to be extended and expanded, the anomalies had to be compelling enough to survive scrutiny from a review board made up of scientists who study everything except our own solar system. They were compelling enough. The program continues. When researchers looked again, this time comparing Webb's atmospheric data against updated interior heat flow models, something else emerged. A possible link between the location of the strongest thermal anomalies and the far side of Sputnik Planitia, the same nitrogen ice plain New Horizons had already flagged as unusually young and smooth. If Sputnik Planitia sits above a region of the crust that is thinner, or above a section of subsurface ocean that's closer to the surface, it could explain both the plane's youthful appearance and the strange atmospheric behavior Webb is now recording almost a decade later. It would mean the most striking feature New Horizons photographed in 2015 and the most puzzling data James Webb has gathered a decade later might be two different symptoms of the exact same underlying process. Everything changed the moment those two data sets were placed side by side. There's a detail in the New Horizons data that took on new weight once Webb's results arrived. Sputnik Planitia isn't just smooth and young-looking. It's also unusually massive for its size, made up of a thick layer of nitrogen, carbon monoxide, and methane ices sitting inside what appears to be a large ancient impact basin. Shortly after the 2015 flyby, several research groups proposed that the sheer mass of that ice deposit, combined with its position near Pluto's equator, might explain a subtle wobble detected in Pluto's rotation and orientation relative to Charon. For that wobble to make physical sense, some of those researchers argued, there would need to be a layer of liquid water beneath the ice shell, decoupling the frozen crust from the rocky interior and allowing the whole shell to reorient itself slightly over geological time, pulled by the extra mass of the nitrogen ice sitting in Sputnik Planitia. It was an elegant piece of orbital mechanics reasoning built entirely on gravity and rotation data, with no atmospheric evidence involved at all. And it predated James Webb by years. When Webb's thermal anomaly map was eventually overlaid onto that same region, mission scientists noticed the uneven heat signature clustered in almost the same area the earlier reorientation models had flagged as most likely to sit above a thinner ice shell. Two completely different lines of evidence, one from orbital mechanics in 2016, one from infrared spectroscopy in 2025, arriving at roughly the same location on the same distant world nearly a decade apart, without either research team initially looking for the other's result. That kind of independent convergence is exactly what makes planetary scientists sit up and pay attention. It's the difference between a single strange measurement, which could be noise, and multiple unrelated strange measurements that all point toward the same physical explanation. It doesn't prove the subsurface ocean hypothesis. Convergence isn't confirmation. But it raises the burden of proof required for anyone arguing the anomalies are simply model error or measurement noise, because now that argument has to explain away two independent data sets instead of one. It's worth pausing here to understand just how strange it is that any of this is even possible. Pluto is a dwarf planet roughly 2/3 the diameter of Earth's moon, orbiting so far from the sun that sunlight takes over 5 hours to reach it, compared to about 8 minutes for Earth. At that distance, sunlight is roughly 1,000 times weaker than what reaches us. It should not, by any straightforward reading of orbital mechanics, be a place where anything resembling active geology survives. And yet here we are looking at spectra suggesting exactly that. Nobody expected this.